Hoang, and my final project was about the fragmentation of lanthanum cyclopentadienol, which is the organic metallic molecules. My specific goal was to figure out the activation energy of the first barrier of the reaction pathway and understanding the paint result with wave packet dynamics and Arrhenius law. The minimum activation energy that I obtained from the MATLAB code was P0, which is initial momentum is in 60 atomic units. The methodology I used in the MATLAB codes were Hamiltonian evolution operation and propagation of the Gaussian wave packet, as described in the slides. It was able to observe the theoretical relationship between the initial momentum and the temperature, that the initial momentum was proportional to the square root of the temperature. One of the most important things done in the class was interpreting the data with Arrhenius law. The Arrhenius law shows the linearized relationship between the rate of reaction and the square root, then the 1 over temperature. As you can see, the natural log of the rate of reaction and 1 over T make proportional relationship in the chemical reaction that it was tested in the equation is applied to our reaction as well. After plotting the graph, we could see that the graph is linear and check the Arrhenius law would apply to my reaction as well. And from the Arrhenius plot, we can derive the activation energy of the reaction mathematically. We can see the slope of the plot of negative activation energy over R. If we multiply R to the slope, the activation energy can be derived in the unit of the electron volt. And the remaining activation energy of the reaction is 0.474 electron volt. To summarize, it was able to observe the activation energy of the fragmentation of LACP, which is the molecule of my interest, and also was able to see the reaction fit into Arrhenius law. Thank you.
Let's end the speaker. And the presentation is open for discussion and questions.
So the barrier is 1EB or